Hello, welcome to another lecture. So this one is titled The Earth in Space. So in this one we're going to talk about and give you an introduction to the solar system and where the Earth fits into our solar system. Okay, so this opening slide is an image of what's often called our sister planet. So it's not the Earth, this one is Venus. Venus is our closest neighbor in terms of planets. Very similar in size to Earth, about 80% of the volume of Earth, so somewhat similar size. And this image shows Venus with the very thick atmosphere it has stripped away. So what you see is this what's called different colors, what's called a digital elevation model, shows different elevations. So these kind of pinks and reds are the high, what looks like a mountain range, and the blues lowland plains and basins. So in these mountains, you can see these large fissures or clefts or fractures, and they're essentially rift valleys and faults. And it shows that Venus is still tectonically active. It has active volcanic activity and volcanoes on its surface, much like Earth. But Venus, normally you wouldn't see this if you do a flyover, because it's enveloped in a very, very thick atmosphere, which is something like 100 times as massive as the Earth's atmosphere, composed of mainly carbon dioxide, CO2, but also thick clouds of sulfuric acid. So very inhospitable, if you will, to certainly to humans or life. But the surface temperatures, we've had probes which have been sent to the surface of Venus and directly measuring the temperatures. And the surface temperature is something like 900 degrees Fahrenheit or 475 degrees Celsius. Very, very hot. And that's because of these thick carbon dioxide rich atmospheres, essentially runaway greenhouse effect. So these surface temperatures are actually hotter than Mercury, which is the closest planet to the Sun. So there's Mercury, the closest, then there's Venus, and then Earth. But yeah, very, very hot surface conditions. All right, so let's put Venus and the Earth in context with the rest of the solar system. So here's your classic image of the solar system. All the planets of the solar system, 8 planets. There used to be 9. We used to count Pluto, but that was demoted to a status of a dwarf planet back in 2005, I think, by NASA, essentially because other very small planets and planetesimals were starting to be discovered in the outer solar system, but not quite given the classification of a planet, these small objects. So yeah, the 8 planets all orbiting the Sun, roughly mainly on the same axial plane around the Sun, and forming this big disk, rotating disk of planets. And there's 2 sets of planets we'll talk about. So there's the inner sort of rocky Earth-like planets. So starting the innermost is Mercury, then we go outwards to Venus, then Earth, third rock from the Sun, and then Mars. Very similar planets, all made of sort of hard, rocky, kind of silicate mineral rocks, similar to Earth. Then you go further out into the solar system, you pass what's called the asteroid belt, which I'll come back to, and then you enter the outer planets. These big gas and ice giants are first Jupiter, then Saturn, then Uranus, then Neptune. And Jupiter and Saturn especially are huge, massive planets. This isn't drawn to scale. They're much, much bigger than the inner planets. These huge things have huge gravitational forces because of that, just themselves. And talking of gravity, that's what, going back to the asteroid belt, this essentially this debris that's left over from the formation of the solar system 5 billion years ago. So when the solar system formed, this maelstrom of many, many thousands of collisions and material, rock and ice, orbiting the early Sun, lots of collisions between them. What was left over once the planets had formed found their way to this orbit quite close to Jupiter, between Mars and Jupiter, and we think that's because of the huge gravitational force attraction of the planet of Jupiter, which kind of keeps it in check in this orbit, most of these in what's called the asteroid belt. These large rocks, anything from very, very small, we're talking sort of meters, up to or less, up to 1,000 kilometers in size, the largest one. Outer here shows something called the Kuiper belt, and it could also show even further out what's called the Oort cloud, OORT cloud. And this is other materials orbiting the sun in the outer reaches of the solar system. And here, though, they're not composed of quite large rocky material. Here it's very fine dust and particles, rocky particles, but also fragments of ice and gases in the Kuiper belt and the Oort cloud. Okay, so that's the solar system. So this said there were two groups of planets occur in the solar system. So we can call them, first of all, the terrestrial, or Earth-like planets, these inner four. So Mercury through to Mars, so Mercury, Venus, Earth, and Mars. They're all small and dense and rocky, made of silicate minerals, much like Earth, with an often an iron-rich core and iron-rich rocks throughout. They have what's called low escape velocities, and the escape velocity is the speed required to escape a planet's gravitational force. Low compared to the huge escape velocities of the outer planets, which have, because of their mass, have very much higher gravitational force going on. Due to their surface gravities, Venus and Earth, the two of the larger terrestrial planets, retain their atmosphere. They can hold on to their atmosphere, unlike Mercury and Mars. We think Mars did. We're pretty sure Mars did have an early atmosphere early on in its Earth's history. We're talking sort of 3-4 billion years ago, and including liquid water and clouds of water. And we know that from actually seeing signs on the surface of Mars which show former erosion by rivers, essentially, and there were former lakes of water. Which is why there's an ongoing search for life on Mars. There has been for some time, because theoretically, with water, one of the main requirements for life, certainly on Earth, there could be microbial, bacterial, early starts of evolution on Mars a few billion years back, because there was on Earth going back 3.5 billion years ago, even 4 billion years ago, we think. The very first earliest microbe fossils have been discovered now. So that's the theory, hence why people are still looking for fossils of these things on Mars. Okay, if you go further out to the Jovian planets, the Jupiter-like planets, Jovian. So we go Jupiter through Neptune, Jupiter, then Saturn, then Uranus, and then Neptune. Much larger, but lower density and gaseous, these big gas giants, as they're often called. Very massive. And huge gravitational forces because of that. Very thick atmospheres composed mainly of gases like hydrogen and helium, but also methane and ammonia. Due to the frigid, very cold temperatures, the Jovian planets contain a high percentage of ice as well, especially the outer planets of Neptune and Uranus. Remember, we're getting much further away from the sun and these outer planets, therefore much less solar radiation reaches these planets, hence the very cold temperatures. So to compare those, on the one slide, there's two sets of planets, the terrestrial at the top and the Jovian planets at the bottom. These are not to scale. Jupiter would be much bigger and Saturn than compared to these inner terrestrial planets, for example. But here you can see the inner planets, and I believe these are to scale amongst themselves. So you can see the larger Earth and Venus, and then smaller Mars and Mercury, but they've all got a similar kind of composition, if you will, of rocky, silicate mineral-rich rocks, very much like Earth. They all have the same structure with a metallic core, iron and nickel typically, core, and then they go through this red area, the mantle rocks, or silicate mineral mantle rocks, rich in iron, and then you go to a crust as well on these planets, so very similar to Earth. The outer planets, the Jovian planets, much different. Completely different, really, in terms of structure. They all do have, yes, they have a rocky core, but then it's different. They go through, for example, Saturn and Jupiter, different phases of different states of hydrogen. So the inner area, because of the huge astronomical pressure, it's metallic hydrogen. Then as you go, the pressure is released slightly. As you go further out towards the surface of the planet, it goes to liquid hydrogen, and then it's gaseous hydrogen near the surface, and then there's huge thick clouds. Atmosphere on the surface. Here on Jupiter, you can see the famous red spot, this huge vortex which has been visible for many centuries now, actually 300-400 years. It's been visible by some of the earliest astronomers could see it. This huge storm on the surface of, essentially hurricane on the surface of Jupiter. The outer planets of Uranus and Neptune, very much ice-rich planets, because of very frigid temperatures. So they have a rocky core, and then they go through an area of ice, of water and methane, and then gaseous hydrogen, and then clouds on the surface. The difference, by the way, why the rocky ones in the middle and the gas giants and ice giants, if you will, on the outer part of the solar system? Well, it's a lot to do with when the solar system was forming. These rocky planets formed from various collisions in the inner part of the solar system. But the sun was constantly emitting, the solar wind and solar radiation outwards away from the sun. The streams of ions moving outwards, and they essentially blew, if you will, elements like hydrogen, helium out to the outer parts, the lighter elements, to the outer parts of the solar system. And that's when these gas giants, rich in hydrogen and helium, is formed in the outer parts of the solar system. So the planet's drawn to scale this time. On the left, you can see the big difference in size between the sun and between the planets, and also the sun is drawn to scale. Pretty much an average, just below average, actually, I think. Size star, just in the certainly in our galaxy. So going back in time, how did all this, very quickly, a summary of how did the planets evolve? How did we form our solar system? Well, it's something called the nebula hypothesis, and this states that the planets formed around about 5 billion years ago. The solar system condensed from a gaseous nebula, these huge clouds of gases and fine particles, which we think actually might be the aftermath of supernova, earlier events, exploding stars. So these gaseous nebulae have quite quickly started to rotate, and rotating clouds of interstellar gases and dust, and formed what we call a solar nebula. And these solar nebulae contracted due to its own mass, its own gravitational forces, and most material collected to the center to form the hot proto-sun, the early sun, and then the remaining material cooled and condensed within a thick, flattened, rotating disk. Early, and we're talking thousands of objects rotating the sun at this stage. And then repeated collisions between this kind of maelstrom of objects, this very chaotic early solar system, produces these formed small planetesimals, and then the planets formed from further collisions and accretion of these kind of sticky objects, if you will, to form the current solar system. And what was left over, what formed the asteroid belt, which kind of was took in check by Jupiter, and has its current orbital position between Mars and Jupiter. Okay, so that's the solar system. That's how we think it's formed, the nebula hypothesis. And what about our closest neighbor in space, which is our own satellite, which is the moon? Well, the moon is thought to have formed as a result of a collision between a Mars-sized body, so and a still semi-molten Earth around about 4.5 billion years ago. So the Earth, maybe 4.6 billion years old. So only in the first 100 million years, there was a huge collision between this, as I say, this Mars-sized object. And the Earth was still kind of semi-molten. We're very early on in the Earth's evolution, only talking tens of millions of years. And during this collision, some of the ejected debris was thrown out into Earth's orbit, and coalesced to form the moon. And so the general characteristics of the moon, its diameter, around about 2,150 miles. It's actually quite unusually large compared to its parent planet, compared to other satellites of other planets in our solar system. Density comparable to Earth's crustal rocks. May have a small iron core, much like Earth. Gravitational attraction, because of its smaller mass, is about 1/6 of the Earth's. Doesn't have an atmosphere because of that smaller gravity. a gravitational force. Tectonics no longer active, but we were pretty certain that there was. Well, we know there was active tectonics, so there was molten rock and lava being formed on the surface in its early period of evolution. The surface has been bombarded by meteorites, asteroid impacts from space throughout its history, but especially in this early chaotic period of the Earth, of the solar system, when there were many objects flying around the solar system. So the lunar surface has two types of terrain we can think of. We can think of the darker areas are called Maria, or the singular mare, and this is the Latin. The word is Latin for sea. These dark regions, fairly smooth lowlands, originated from asteroid impacts early on, maybe 3.5–4 billion years ago, and then they were infilled sometime later, around about between 3 and 3.5 billion years ago, by lava. So these forming these large, very large impact depressions and craters were infilled with molten rock, which forms lava, black basaltic lava, that solidified, crystallized, formed rock around about sort of 3.5, maybe 3 billion years ago. So that's the Maria. The highlands, so the lunar highlands were these bright, densely cratered regions, the lighter areas on the moon. If you looked up at the moon through a telescope, make up most of the moon. So here's a better image. You can see all that. So here you can see most of the surface area is composed of these lunar highlands, pockmarked by many hundreds, if not thousands, of impact events from incoming asteroids and meteorites. And here you can see the dark Maria, former impact events, which has been filled up by lava. A couple of famous named craters: Copernicus crater here labeled, Kepler crater. And here you can see on Copernicus crater, you see these lines of material. This is ejecta. So when this impact event happened, when the Copernicus crater was formed, material was ejected out, and sometimes it formed these strands, these lines, and these are called rays, which I'll come back to. Formation of these lunar Maria. So here shows in very large objects were flying around the solar system early on in its evolution, and they were striking the moon at that time, forming these large mare or Maria plural and depressions. And then around about sort of 3.5 billion years ago, so sometime later, they were infilled by liquid rocks, so lava, which had been magma underground. So magma, we haven't come across that yet, but magma is molten rock underground. It gets to the surface, we call it lava. And they form these large dark areas, these Maria. Here you can see also on the lunar surface these very obvious craters. You can see through a telescope. Certainly, most obvious features of the lunar surface are surrounded by ejecta material called ejecta simply, and form sometimes these strands, these occasional rays, especially with the younger craters. Here you can see a large crater, 20 kilometers wide in this case, and here this one has what's called a central peak. And you can put different types of craters into what are called simple craters, where they don't have this central peak, and what are called complex craters, which have this central peak formed during the impact event. Finally, the surface of if you were to go down to the surface of the moon, it does have sediment of different sizes, but especially the finer material, lunar dust. And here you can see an image from one of the early landings on the moon, the Apollo missions. So there were several landings on the moon. Apollo 11, 1969, was the first sort of manned craft to land. Neil Armstrong was the first astronaut to set foot on the moon. And the last mission was in 1972, just a few years later, the Apollo 17 mission. There hasn't been a manned mission since that time. This image, some people out there still think, by the way, it's just a big fake. It's a big Hollywood set. So I'll let you decide on that one. All right, so I'll finish by saying do watch this YouTube. So I'll put a link here to a very good, well-produced sort of mini documentary produced by NASA. It's only 14 minutes long, and it gives you a lovely tour of the solar system. It goes through all the planets, including the asteroid belt, etc. Very visual and well made, so it's very worth watching. So do have a look at that. a tour through our solar system. And I'll leave it there. Okay, thanks for joining me, and I'll see you again.